So let us start. Welcome everyone to this second webinar of Earth Education Collective project. Hope that more people will see this webinar in a record. And we will continue where we end up previous time. Let me share my screen. I will start with a general presentation, and then we will try something live in the internet. So today we will speak about multi-spectral imagery. Let me go a little bit deeper. What does it mean? Last time we have already learned, we used this Global Forest Change portal by the University of Maryland to learn that instead of standard Google background, you could choose the alternative background of Landsat imagery, which are presented here in so-called false color. And these false colors, as we learned, could be sometimes much more informative rather than just standard Google Maps or Yandex Maps background. So you could learn much more about the vegetation, about the land cover, looking at these false colors, like in these two examples I demonstrated last time for tropical countries, for Southern Vietnam and for Western Africa. But why do we see that some of this information somehow, why it is more informative? It is partly because we're using the light, which is invisible by our own eyes, the infrared lights. Let me start, let me remind you a little bit about this very basic stuff about the electromagnetic spectrum. I hope that you already know from your school classes what actually visible light and infrared light and ultraviolet light and radio waves, all of this is just different kinds of electromagnetic radiation, electromagnetic waves, which are basically the same in its nature, but just they only differ by the frequency of a frequency and the wavelengths. But generally, the radio waves and the visible lights and X-rays, all of them are the electromagnetic waves. And actually, the visible light actually is a very, very narrow, I would say, narrow band in this spectrum. So with our own eyes, we could only see a pretty narrow, a little part of this electromagnetic spectrum. So our eyes, our biological nature is adopted to see, to somehow to sense only particular part of the spectrum, and by the way, pretty narrow. And modern satellites and the sensors, instruments installed into these satellites could detect and could sense much wider spectrum of electromagnetic waves, at least all visible light and also pretty wide spectrum of so-called infrared, which is much wider rather than visible lights, and also sometimes a little bit of ultraviolet as well. So if we would look at the spectrum of our sun, actually our sun, the sunlight coming to the Earth, it is also not only visible light. Although we see the sun in yellow, because in yellow it has a maximum of its radiation, but actually also our sun emits the radiation in pretty wide spectrum of electromagnetic waves. It also, as we all know, of course, it emits the ultraviolet, and it emits also the pretty wide band of infrared light. But not all of this light could reach the Earth. For you, in this picture, you could see this yellow. In yellow, there is a spectrum of solar radiation on the top of the atmosphere. Somehow, if you look from the spaceship to the sun, and if you could measure the radiation coming, approaching our planet from the sun, you will see this yellow light. So the most intensive, the most strong radiation is invisible part, especially in yellow part of spectrum. But also, if you would install the sensor and measure the intensity of the solar radiation, it is also pretty intensive in ultraviolet part and in infrared part. So approximately only a half of energy coming from sun to our Earth is coming in this visible light spectrum. About a half is coming in a form of infrared waves and is ultraviolet. Of course, we all know that more or less, but also it's interesting that not all of this radiation could reach the surface of the Earth, because our atmosphere, some gases in the atmosphere, they absorb some part of the spectrum. So some electromagnetic waves of certain lengths could be absorbed by some gases which are in the Earth's atmosphere. We more or less all know, I hope, that, for example, O3, the ozone gas, which is accumulated in the upper part of the Earth's atmosphere, consumes actually a lot of ultraviolet waves, ultraviolet radiation from sun. And this is very fortunately, because if it would not consume it, then the life on Earth would be really difficult and probably impossible on land, only underwater. So with all three, it is pretty thin layer of all three, which consumes a lot of ultraviolet radiation. Also, some other gases, particularly the water, evaporated water in the atmosphere, and just oxygen and CO2. All of these gases, they absorb different parts of infrared radiation. You see this red graph, the red line, red area in this picture. It's somehow reflects the parts of the electromagnetic spectrum which could go through atmosphere. So this is so-called atmospheric windows for solar light. So you see that some particular wavelengths are practically 100% absorbed by the water in atmosphere, by O32, O3, by CO2, by different gases, atmospheric gases. But the rest could go through atmosphere and reach the surface of Earth. And so you could see the sun also, sun radiation reaching the Earth's surface. It is also not only visible light, but also part of ultraviolet and infrared light. So in principle, the general scheme, general way of how the optical remote sensing works looks like that. This is a very primitive picture, but the sun radiation is going through atmosphere and is partly absorbed by the atmosphere. This blue line here somehow reflecting that part of sunlight which does not reach the Earth's surface. Part of it is absorbed by atmospheric gases, and part of it is scattered in the atmosphere just because the atmosphere is not totally transparent. It is not only gases, but also many small particles and like dust and small particles of liquid water, which are almost in the atmosphere, and they scatter at some part of a solar light, mainly the blue, in the blue part of spectrum. And this is why our skies look blue, because this part of light coming from sun is scattered in the atmosphere, and the rest is reaching the Earth's surface, and part of it is also absorbed by different kinds of surface, and the rest is reflected back to space, and part of this reflected solar radiation could be detected by satellite sensors and recorded. So this is how satellites could learn something about the Earth's surface. They only, let's say not only, but mainly gets the sunlight, detect the sunlight reflected from the surface. Of course, the real picture is a little bit more complex, because also some warm surfaces, they also emit the infrared radiation by themselves, but let us come later to that. So again, just to remind you that only this very, very narrow part of electromagnetic spectrum is visible by our eyes, and the satellites could detect more than we see. And if you will, this part of a spectrum which is now inside of this circle, this ellipse, if you will just zoom it to the whole screen, we will see the picture like that. By the way, this particular picture I took from NASA website telling about Landsat satellite series. You could also go there and learn a lot about these satellites. So we also see this gray background in this picture is that atmospheric windows. The intensity, all these peaks, gray peaks in the background, they reflect the atmospheric transmission. So the light which goes through the Earth's atmosphere and through these atmospheric windows. And you see that some wavelengths are totally absorbed or nearly totally absorbed by the atmosphere, but the other lengths could very easily go through and reach the Earth's surface, reflect from the surface, and go back to the space. And then the satellite, the sensors installed in the satellites, they could detect this light reflecting from Earth's surface. And in the most of the modern optical satellites, the sensors installed, they could detect separate parts of the electromagnetic spectrum and record them separately. So all these blocks, they show here the so-called spectral bands. So the narrow stripes of electromagnetic waves, which are detected by particular sensor on board of satellites. So there's a few, here a few satellites are presented. All of them belong to Landsat series. This is a series of NASA satellites for Earth observation, active for already a few decades in the orbit. Of course, they are a little bit different because the development, the technology is going to develop more and more. And for example, these cameras called MSS camera installed in this Landsat from number 1 to number 4. It only records, as you see, the visible light and only some part of the infrared. Then on the Landsat 5, which worked in the orbit for more than 15 years, nearly 20, we also see that these bands are located in other parts of the infrared spectrum. So we could see some infrared parts, some infrared light which is not detectable, not visible, neither by eyes or by detectors in the previous Landsat satellites. This is Landsat 7, which is still operational on orbit. And this is spectral bands for Landsat 8 and 9. So what kind of bands it is? Yeah, by the way, all these strange abbreviation like MSS, OLI, TIRS, all of this is just the name of instruments, the names of sensors, let's say digital cameras installed in the satellites. They have that kind of different names. You could, of course, go to this Landsat website and read much more details of how does it work, how they look like, and so on. So what actually spectral bands, what parts of electromagnetic spectrum modern satellites actually record? Let us, today we will tell only about this Landsat series satellites. But of course, this is not the only one available nowadays, not the only one operational. It is just one of the most common data you could find everywhere, and the set of data which is freely available now. So first of all, here, all of these bands is a visible light. Basically, there are three main visible spectral bands. This, I will call them by number 2, 3, and 4. So 2 is detector for blue light, 3 is detector for green light, and 4 is detector for red light. As you see, practically all Landsat series satellites were equipped with these 3 detector, this 3 sensor. Also, usually starting from Landsat number 7, you could see so-called panchromatic band. What is it? It means just recording all visible light, or sometimes visible and some part of infrared light, all together without separation for blue, green, and red. So just, it is like a black and white picture, like an old black and white television. You will see all the light all together. So you detect only brightness and without separation for blue, green, and red. Whatever light is coming to the sensor, that kind of light is recorded. Its intensity is recorded. Then also you see that practically all satellites, starting from the very first Landsat satellite, have been equipped with so-called near-infrared detector. So this abbreviation NIR, NIR. It means near infrared, so-called the infrared light, which is very close to visible. It is already invisible, so the human eyes cannot see it, but it is pretty close in wavelengths to visible red. So it is located closely. Also, this is even two bands starting from Landsat 5. There are sensors, detectors recording infrared light in these two atmospheric windows, in these two peaks. And this is so-called short wave infrared. This sphere, SWIR, this is the abbreviation for this short wave infrared. It is the kind of medium length infrared light. So it is not close to visible, but not very far from visible. It is somehow in between. But it is also very, very important, for example, to detect vegetation. And there is also so-called thermal infrared detectors. In Landsat 8 and Landsat 9, there are two separate bands to record different parts of this thermal infrared. This is so-called thermal, or sometimes it is called far infrared. So it is far from visible light. And what's important that this thermal infrared, it is the radiation emitted by virtually any warm or hot object on surface. So it is not so much in this part of this far infrared, thermal infrared spectrum. The sun light does not play sufficient role, actually, because the sun does not emit much in that part of the spectrum. So what is detected by sensor of satellites? It is mainly the radiation, the infrared radiation coming from warm surfaces, or somehow with cold surfaces, but it's just a question of energy coming from different temperature surfaces. So this part of infrared spectrum is very important also because it is practically a kind of distance measurement of temperature, which using these satellite instruments, we could measure the temperature of the Earth's surface. So also you could see that this latest Landsat 8 and 9, latest Landsat, we also have some specific channels like this Spectral Band 1, which is so-called ultra blue, practically very close, visible light very close to ultraviolet, and with band 9, which is also narrow band in infrared channel, and exactly in the area which is mainly dispersed or absorbed by atmosphere, this light. So it is mainly used for detecting, for study atmosphere, for study clouds, for study this very thin so-called cirrus clouds, and so on. So this is a little bit specific instrument. Just let us not pay too much attention for this now, but at least you should know that there is a very important this visible light, is near infrared, short wave infrared, and thermal infrared. This is the main bands, main spectral bands, main spectrum of electromagnetic waves, which are recorded by detectors installed in the Landsat satellite. So this also you could find even in Wikipedia, or of course also in NASA website. You could find all these details when exactly which is exactly wavelengths for each band, what is the name, what is the number of that band. So you could just go and find this information practically anytime you would like. of course, I also will share this presentation with you as well. So, but what's also important that different objects on the Earth's surface reflect and absorb sunlight differently. So the sunlight is going through atmosphere, partly absorbed by the atmosphere or scattered in the atmosphere, but the biggest part is reaching the surface of the Earth. And here surface different objects on Earth. They differently absorb and reflect different part of a spectrum. So the water, some part of the sunlight is just absorbed, consumed somehow by the water, and just converted to heat, basically. But sufficient part is reflecting back, and after going through atmosphere, could be detected by satellites. And if you would measure what part of a light is reflected, we would find that this part of a light reflected from different surfaces and different objects on Earth, they could reflect strongly or weakly at different wavelengths. For example, different lights here, this is, I just borrowed this from the presentation, which I also recommend you to download and go through. This is a very simple presentation about Landsat imagery done by NASA and distributed by NASA. So it is just a picture. You see that, for example, water, they reflect sufficiently in a visible part of light and near infrared. But if you move further on, you will see that reflection of water is not sufficient in the, for example, in shortwave infrared or in far infrared part. So the biggest part of that electromagnetic waves, biggest part of that light is absorbed by water, converted to heat, but not reflected back into space. But also you could see, for example, snow and ice and clouds, where clouds are very white and they reflect nearly all light back. So equally good reflecting visible light and near infrared and shortwave infrared and even thermal infrared. But also different types of vegetation, they reflect differently, different parts of waves, different waves of different lengths. And this is one of the main way to distinguish different type of vegetation from each other. So I just took one picture from one of the scientific publication of my colleagues who just presented with graphics of so the intensity of reflected radiance for different bands of Landsat. Here down, you could see the blue band, green band, red band, near infrared band, shortwave infrared, and this is Landsat 7, the previous Landsat, but still operational. And you could see that comparing the intensity of radiance detected by this sensor by this sensor in different bands, you could find the difference between water, background, vegetation. Also, even you could see difference between tree vegetation and grass vegetation, between coniferous and deciduous trees. So you could learn quite a lot by studying this information from different spectral bands. But also see, if we could take a look only for visible lights with blue, green, and red, you could see the difference in the intensity of reflected radiance is not so sufficient. But in this invisible infrared part, different objects reflect the sunlight really differently. So you could see very big difference between water, background, tree vegetation and grass vegetation, for example, in near infrared and short infrared light. And also in invisible part of a spectrum, the red light is the most important. So this is how we could learn remotely about the nature of a surface of our planet, which reflects different land cover classes, different vegetation types reflect differently sunlight at in different parts of the electromagnetic spectrum. So by detecting these in different spectral bands and recording it separately, we could learn a lot about our surface of a planet. Actually, also you could pretty easily, if you could just look, you could find a lot of recommendation also, by the way, in Russian language. You could find recommendation of what spectral band is the most useful for what purposes. Like you see the band 1 is ultra blue in Landsat 8 and Landsat 9. It is mainly used for coastal studies of shallow water. You could see the plankton algae, a chlorophyll of a plankton organisms could be seen in the spectrum. And also you could study aerosol in atmosphere using that band. For example, if you would like to study vegetation, that's the most important for you are the band 4, band 5 near infrared, and 6 and 7 with shortwave infrared. If you would like to measure the temperature of objects, then the thermal infrared lights are the most important for you. So different studies require different using of different spectral bands. So again, the same picture. I could come back to this picture just to remind you that this is only these small parts is a visible light, and all the rest is invisible infrared light. But also how you could, of course, the detectors installed in satellites, they detected this light and recorded it, and how we could study it. First of all, usually you would like first to see these images with your own eyes. So how all these other bands, which are usually invisible, how they could be visualized in as a visible picture. So somehow, how could we make these bands visible? Because the records, it is this satellites, they only records the intensity, and all these records were basically figures, the intensity of radiation recorded and measured in figures and recorded. So how does it work in the most of cases, in the most of geographic information software? And we will also now learn how to use it by ourselves. So you know that in the most of monitors in our computers, these colorful pictures in our screens, they are basically produced by combination by three different colors: red, green, and blue. If you have ever worked with computer graphics, you should know this RGB synthesis images. But basically, each small pixel in our screen, it has basically three light sources where diodes which emit some blue light, green light, and red light, and mixing these three colors in different proportions, you could see the colorful pictures. It is, if I'm not mistaken, this could be something like 24 millions of colors in the most common screen. So this is how we could also do. We could select just any three spectral bands. If you will just show them as a picture in the computer screen, they will be just black and white. We could reflect the intensity in one band with only one color. For example, like black color, it will be just gray picture with many shades of gray, which could show you the intensity of this reflected light in this particular channel, only in red or, for example, near infrared or in thermal infrared part of spectrum. But actually, you could present it not necessarily in gradation of gray colors, but you also could present the intensity of this radiation in gradation of blue or in gradation of green and red colors. And if you could take three different spectral bands, color one of it color blue, another of it you could color green, and the third color red, then you could combine it in your screen with RGB color composite, and you could see then the colorful picture. If you would select the visible blue and color them in blue, select visible green and color them in green, select red and color them in red, you will see more or less so-called natural colors. Not actually exactly, because you have seen in the previous picture that these bands, they do not cover the whole spectrum of visible light. And also this so-called green color, it also could include some yellow, for example. And blue, it is not only blue, but also light blue, dark blue, and some violet all together. It could record. So this will be not exactly the natural colors. It is so-called pseudo-natural. And this is what you see in Google Maps, in Yandex Maps, in Microsoft Bing Maps, in all of these common portals. You could see these natural or pseudo-natural colors, which is produced using this combination of usually these first three channels of Landsat and first three channels of some other satellites. They use only visible channels for visualizing the picture. But we could do also in another way. We could take not three visible spectral bands, but you could take, like, for example, near infrared, shortwave infrared, and thermal infrared, and you could combine them in a different combination. You could color them differently and produce this color composite using different part of spectrum. And of course, these colors will be not natural. It is so-called false colors, but you will, in that way, you will visualize the infrared bands, which otherwise would be invisible. So what I would suggest now to do, you could, if you are sitting at the computer, you could also find the same portal called Sentinel Hub. I will now maybe interrupt my presentation and copy this link to you to our chat. So you could open it. It is also a free portal which does not require registration for simple operation. If you would like to download later, when you will need to register, but still it will be free. So what I would suggest to do, when on all of these kind of portal where you deal with satellite imagery, you have, if you would like to visualize some particular satellite images for particular areas, you could go through 3 simple steps. Step number 1, you select actually the source of images, select the satellite. By default, there's actually a list of satellite data available in that EO browser in Sentinel Hub. By default, it is selected Sentinel-2. It is another satellite by European Space Agency. You could come to it later. It is even maybe more advanced in many extent, but you could let us just choose Landsat 8. And basically it doesn't matter, is it with level 1 or level B or level 2 of processing. It is just, basically it is a light detected on the top of the atmosphere, or some extrapolation how this light would be if we would remove the atmosphere. So let us, I would suggest to start with level 1, but hardly you will see the difference if you also use level 2. So step 1, select the satellite. Step 2, you could select the area. In this particular picture, I selected the Adirondack Mountains in the United States, in the state of New York. It's close to Great Lakes area. And then step number 3, you have to select the time range, time period for which you are looking for satellite images available. We will come later on in the next our next webinar. We will come to this time sequence and multi-temporal imagery. But for this particular part, you could just select for like 1 month. I selected here the August images for August, for summertime, for vegetation period. So if you would like to see vegetation, better to select some vegetation period, summer period in the Northern Hemisphere. In the tropics, it doesn't matter. If you would like to see something else, like snow cover, for example, then you could choose another time range for study. And then you could just search, and you will get the list of available images. You could also, by the way, if you two-step back, you could also select the cloud coverage, maximum cloud coverage limit. So to sort out the scenes which are too cloudy. So again, 3 steps. You select the satellite, you select the area, you select the time range, and when you search, you will get the list of images. You could select one, basically anyone, and click this visualize point. I will show you this also on my own computer, but now I'm just showing the presentation, the picture. And then you could see this image by default. It is a natural colors combination. As you see, it is also like pretty dark, brown, brown and gray mainly at that scale. So you do not see any much details about the vegetation. But there is other combination of spectral bands available, and particularly it is a combination, the custom it is called the custom combination of bands. Let me now show it live on my screen, on my own computer. I will stop the presentation and we'll go to this browser, Sentinel Hub portal. So again, first we choose the satellite. I will not choose Sentinel-2 now, but we'll choose this Landsat 8. And I will choose the level 1, level 2 I will skip. And let us set up some more or less cloud-free images. This is step 1. Step 2, let us select the area. Let us this time select some area on the Russian side. For example, some area in Russian Northwest. Like for example here. So you could use this tool to draw the area of your interest, but also you could use the extent of your screen as a study area. But also you would like to, if you would like, you could draw particularly smaller area, or you could just, not necessarily it should be rectangular, you could just draw some polygon delineating the area of your interest. And then if you scroll down a little bit, you could select the range. Okay, by default it is the last month, but it is so fine when also it is already pretty cold and maybe already snowing. You could just select, let's say, let us select again the August, from 1st August to mid-September, for example. And then search. And you could see different images. Of course, they are not totally cloud-free. So this is, you see that there are some clouds, but I visualized it. By default, it is a true color. Also, you could use other options. There is so-called false color when you combined these bands 4, 5, 4, and 3. So probably it is a numbering for Landsat 7, so it means that it is near infrared, visible red, and visible green. So you could see different picture. Of course, the colors here are not natural; these are false, and all of this picture looks like red. But I would suggest to use this custom combination. As you would press custom, you will have a choice. You see here are the spectral bands of Landsat 8. This is that 9 spectral bands here. And down there, you could choose 3 of them. You see here it is by default, they are chosen band 1, band 2, and band 3. This is blue, another blue, and green. So if you would like to study vegetation, you should remember that the biggest difference in vegetation is in red channel, near infrared channel, and short infrared channel. We could just come back to our presentation, or you could refer to any website, find this information in the web. We see the biggest difference in vegetation is in near infrared and shortwave infrared and another shortwave infrared, and also some difference in green, in red, visible red. So what numbers there are? Visible red is 4, invisible near infrared is 5, and shortwave infrared is 6. So let us choose these channels here. 4, 5, and 6. We will color band number 6 as red. Band number 4 you could just drag and drop. Band 5 will color green, and visible infrared we will color, visible red we will color blue. And we will get this false colors vegetation. Let me switch off. So you could see very big difference in different types of vegetation. As you would zoom in, you will see this darker green areas. It is probably coniferous forest. There's different kind of light green. It is probably deciduous and mixed forest. And we also see different colors for boggy vegetation. Some wetlands. If you, for example, zoom in here, let us wait, it will be a little bit more clear. You will also see different type of wetland vegetation. So if you would like to learn in more details what color combination actually means what, I would suggest you to go again to this global forest forest change website. And again, if you would use this background imagery for 2020, here it is cloudless composite. It is not just one imagery. It's many images combined together. But also this combination is also 3, 5, 3, and 4. But it is a number of spectral bands for Landsat 7, which is a little, Landsat 7 had a different numbering comparing to Landsat 8. So 5, 3, and 4, it is the same like 6, 4, and 5 for Landsat 8. You could, by the way, also choose another combination here, just using this near infrared, one shortwave infrared, and another shortwave infrared channels. Also, you could see that's another combination. And when you could zoom in your area of interest, study here different vegetation types. How different land cover classes, different type of earth surface, how does it look like? So also it's important that we could use it at the same time when here the satellite, high resolution satellites in natural color from Google Maps, and with alternative color images. So I will switch to this selection back. For example, you see here in Google Maps, you see some croplands, some fields, some agricultural areas, also some maybe it is abandoned fields or just grazing area, some natural vegetation along the channel. You could see some water objects, some background, and when you could, if you will turn on imagery, you will see also some difference. You could see the water is black, clean water is black here. They also you could see that this is also water in with white color. So where these croplands are green, natural vegetation is green. And here this is a signal from somehow this is a very sparse vegetation. Probably it is a signal from background with some sparse grass coverage. So let me for a moment come back to the vegetation, to my presentation, I could just show you just a few pictures of different vegetation type from different parts of North America. Like, for example, this is from Canada. This is the Fraser Plateau in British Columbia. Oh, sorry, it is, yeah, Fraser Plateau, it is in British Columbia. And you could also see dark green coniferous forest. You could see some, in magenta, you could see probably some fire scars, burnt areas. You could see some logging in clear cuts and in with pink and light green. Light green, it is where deciduous soft hardwood forest coming back after logging. So you could see different type of landscapes, and also with black you see also clean water lakes in black color. That's another type of forest, which is tropical moist forest in Mexico, in Veracruz region. So this is like light green color. You could see this deciduous forest were different in reflection in this infrared and visible red channels rather than coniferous forest in the north. Also this mountain area, it is in British Columbia again, with the highlands. You could see in these highlands with snow and ice on the top of the mountains. They are reflected in white and blue. Mainly they have wet kind of colors. You could also see some, the right side, you could see some violet areas around with glaciers, around with snow areas, which are free of snow, but they are also free of vegetation. It is also so-called mountain tundra vegetation, which is very, very small shrubs growing there. But you could see also in the valleys along the rivers, you could see different types of mainly forest vegetation, mainly coniferous, and some deciduous. Just maybe a couple of another example. This is along the Columbia River. This is a practically treeless area, which is a grasslands and shrub, so-called shrub steppe. And in the summertime, all these grasses are mainly dry, and you practically see the bare ground here. You could see this red and magenta colors, different kind of colors, which is mainly reflectance from bare ground with a very, very sparse and poor vegetation. And all these green spots you could see, it is mainly agricultural areas, croplands, or some maybe populated areas with some trees, planted and watered artificially. So it is completely other landscape. And finally, this is very, very northern area, Canadian Arctic tundra. Here you could see also very little of tree vegetation, only along the rivers. But also you could see different kind of grasslands, northern grasslands and wetlands reflected here in different kind of green and red and brown. So you could go to area, zoom in and study with also these detailed images, how they look like. Then we could, to finish for today, I could come back to this Sentinel hub, and actually you could play here with spectral bands. You could find some other combination of spectral channels. For example, you could use some shortwave infrared you could use it instead of visible red, for example, and you will see some other information. Here it is not much difficult, but also some types of vegetation looks differently. And also you could see more clouds, by the way, here. In the original image, you did not see any clouds as well. Or you could choose all of this. You see this as a combination of different kind of greens. Also, you could see vegetation, but you also could, for example, use some other bands. Yeah, maybe it is not the best example, but let us take something completely different. This is because of, for example, 9 we could use as a green. Here we have, you see, in that combination, when you use this far infrared channel, you practically do not see the vegetation, but you somehow could practically see a little bit of temperature. That the clouds, they are more cold, and so they are white here, and you could see also different kind of clouds, but practically do not see details in the ground, details of the vegetation. So different band combination you could try to study different objects. So in this combination, you could see better the surface. So you could play a little bit with your area. And what I suggest you to do during the next week, just to find this image, use this Sentinel Hub browser to study images for your area and to try different band combinations. You could surf the internet and find more information about what combination of channels, of what combination of spectral bands is recommended for studying what kind of objects on the Earth's surface. You could play a little bit with that and try to make a picture of your area. I think I still like this combination the best. Is to study vegetation. Here, let us wait. It takes a little bit of time. And if you would like to save it, actually, you could save a picture. To just save a wait, where is it? Yeah, he's download the image. If you are not registered, you could just download as in JPEG as a picture, but you could do it. And so you could use JPEG or PNG format, download it and save on your computer and send it, for example, to us, and with explanation what do you see in that image. So this is our first step to choose your area for your project and make the color, this false color satellite image for that, and try to find the spectral bands combination which would emphasize the objects you are going to study. If you could study vegetation, but probably this 6, 5, and 4 combination is the best. But if you study something else, some human-made infrastructure, for example, or some waters and sediments in the waters, or some turbid and clean waters, or some oceanic studies or atmosphere, so you could select other band combination. So I think we are already running out of time. I'm speaking for already an hour, so I will stop for now, and I'm open for your questions. Right now, you could ask or you could ask later, write to me. And of course, the record of this webinar and the presentation I show it you will be distributed maybe tomorrow. I will send out all of this information. So any immediate question, you are free to turn on your microphone where I'm not blocked and speak or write as you wish, as you prefer. Any questions for right now? I understand that in some eastern regions it is already late now. But anyway, so if there's no questions now, you could feel free to ask any questions later. I do recommend you to try this Sentinel Hub browser for your study area and start to think what actually you could see with satellite images. So if no questions, so I thank you everyone for attending, for spending your weekend time for listening to me, and hope to see you again. Hope more people will see this presentation in records, especially in the easternmost regions of Russia, where it is already deep night now. I'm sorry for this inconvenience. Thank you again. Good luck.